Okay, another known cross-section that I've seen used, or that we use once in a while, are isosceles right triangles with a leg on the xy plane. So I drew a sketch over here. And again, this is example 6C, so we're using the same basic setup as example 6, except we're going to talk about an isosceles right triangle rather than a square. So the area of a triangle is 1/2 base times height. Well, since the legs of an isosceles right triangle, they're both the same, and they are perpendicular to each other, because they form the two legs of the right triangle, and we have the hypotenuse. They actually form the legs of a right triangle. Okay? Or they are the legs. In other words, we can use one as the base and one as the height. So the area of an isosceles right triangle is just the same thing as 1/2 leg times leg, or 1/2 leg squared. That's the same thing as base times height. And in this case, the leg will be the top curve minus the bottom curve, or 2 times the square root of 4 minus x squared. So this is the same. So I just put this in our formula again, going from -2 to 2 of 1/2 leg squared. And this is my leg. Now again, what I can do is I can change this from -2 to 2 to 0 to 2 and double it, because it is symmetrical still. And then we can square this. 2 squared is 4, and then this is 4 minus x squared. And then either way, this cancels, and I have a 4 in front. This becomes 1, or I got 2, and 2 is 4. Either way, times this. And I can use the 4 in front, and then I can just take the antiderivative, which is going to be 4x minus x cubed over 3 from 0 to 2. Again, we zero out, because we have factors of 0 in each term. So 8 minus 8 thirds, and there again, almost the same. 16 thirds, except for times 4, so it's 64 over 3. Okay? So a lot of similarity between these, because I'm using the same setup, just showing you the different types of cross sections, so you get a good feel of those. So that's an isosceles right triangle with a leg on the xy plane. Okay? All right, now I've also seen an isosceles right triangle with a hypotenuse. So this will be example 6D. So we're really going to get our money's worth out of example 6. Okay? So this is 6D. And this is an isosceles triangle with a hypotenuse to be on the xy plane. Okay? So again, this is our basic setup, the area. So I got to figure out the area. So how am I going to figure out this? Well, we talked about the area of a isosceles right triangle being 1/2 leg squared, right? That would be leg times leg. Okay, so this is going to be my hypotenuse. So my hypotenuse will be this top curve minus bottom curve. So h, I call it h hypotenuse, and these are the two legs. There's the right angle, so you can see the hypotenuse is on the curve there. Okay, around the circle, or the chord. Okay, so h equals this, top curve minus bottom curve. And I know from the Pythagorean theorem that L squared plus L squared equals H squared. So 2L squared equals H squared, and H squared is just this squared, which would be 4 times 4 minus x squared. Then if I divide both sides by 2, I get L squared equals this. But remember, the area, A sub x, is the area of the triangle, which is 1/2 L squared. So if I take 1/2 of this, L squared, I get 1/2 of this, which is just 1/2 of 2 is 1, so just that. So that's the area. So it works out pretty nicely when you do it like this off on the side. Okay? So the volume equals, again, from -2 to 2 of my area. So again, I change it to 2 times 0 to 2. And this is my area. Nice, isn't it? Okay? So 2 times, and then if I evaluate this is 4x, again, x cubed over 3, so we have the same thing. And then we've got 8 minus 8 thirds, which is 16 thirds, but only this time times 2. And we get 32 thirds. So you can see a lot of similarity, although the answers all come out just a little bit different. Okay? And that was good old example 6D. Okay? Now we're going to do some. Now all these have been with respect to x. Now we're going to do some with respect to y. Oh, this is one more with respect to x. I got one more with respect to y. Sorry. This is cross-section perpendicular to x-axis of a rectangle, so this is a new setup for problem. Now, I've seen these done before, and even on the AP exam, I think I saw one of these like this. Remember, we have to be able to write the area in terms of this distance. This is the only variables we have. So how can we do rectangles? Now, we do squares because the size of all the squares are the same. But we can do rectangles if the height is always the same. Okay? Because the base of the rectangle will change. So unless we have a ratio, we could have a ratio between the base and the height. That would also work. All right? We have to have some way of tying this in and making it one variable. So this is a method I've seen. The height is 2. So these rectangles are all have the same height. Okay? But the bases change. Okay? And it's interesting to see how this looks. So I'd like to get a 3D rendition of this so you can see. But the heights are all the same. So basically the bases change. All right? Now also I changed the base of this figure. It's still going to be in the xy plane. Okay? But the bases run from the line y equals 4 to the parabola y equals x squared. So there's your parabola x squared. This is your line y equals 4. So this is going to be the base of this solid formed by these rectangles. Okay? So the base, so this is kind of the bottom of my solid. I don't want to use the same term twice. So for my rectangles, okay, the base of my rectangle will be the top curve minus the bottom curve. Okay, that's going to be this distance minus that distance, which will give me that distance. And that's going to be, the top curve is 4, and the bottom curve is x squared, so it's going to be 4 minus x squared. It looks kind of like familiar, kind of like example 6. Again, we've got our 4 minus x squared. It just happened to work out like that. So top curve minus bottom curve, 4 minus x squared. Now, the area of a rectangle is base times height. Now my base will vary, 4 minus x squared, but my height will always be 2. So this is my area. So I just put this in my formula. And again, what I did was, there is a symmetry. So instead of going from -2 to 2, I just right away went from 2 times 0 to 2. So I applied that symmetry. It's the same thing as going from -2 to 2. Because it is between x equals -2 and 2. And I didn't mark that. I guess I could have marked this on my graph as being down here at 2. -2, excuse me, and down here at 2. That's 0. Okay? All right. So again, I've just doubled it, so this is 0 to 2 rather than -2 to 2. And that's my area, and my area is 2 times 4 minus x squared. And then I can take the 2 out, so I got 4, and looks familiar, yeah. We take the antiderivative of this. We took the 2 out to take the antiderivative of that. I get 4x minus x cubed over 3 from 0 to 2. So I got 4 times, and that's going to be 16 thirds, so that's 64 thirds. Okay, so we have 64 thirds for this one. Oops, get this up a little bit higher so you can see that. Okay. So this is a square, but it's just, I just changed the bottom of your solid a little bit so you can take a look at it. I'm sorry, excuse me, not squares, rectangles. Pardon me. So we changed kind of the bottom from it being a circle to it being this little part of a parabola. Looks almost like, upside down Norman window. Okay, so we've got that. Well, not that really, because the Norman window would come down like that. But anyway, it's a little parabolic section there. So we've changed that bottom of our solid, and then we've changed it to this is not a square, this is a rectangle, but with a fixed height. And the bases will change. Okay, so I hope that makes sense.